Good evening, Dr. Ajay, sir.
Yeah, good evening.
Hi, sir.
Hello. So
So,
I'm
in few minutes, we'll start, sir.
sure,
Participants
sure, no problem, no
join
problem,
in.
no
Yes.
problem, no problem.
So, we'll start, sir. It's a short intro about you. We'll start the session, sir. Sir, Ajay, sir.
Yes, you can start.
Okay, sir. So, good evening to all the respected dignitaries, research persons, and the faculty members and participants. So, it's my privilege to welcome you to the day 5 of the AICT Atul sponsored online faculty development program on emerging trends in advanced materials, smart fabrication techniques, and precision metrology. Today, we are delighted to have with us Professor Ajay Kumar, sir, Associate Professor in the Department of Mechanical Engineering at Tirupati. Professor Ajay Kumar sir obtained his PhD in Mechanical Engineering from Indian Institute of Science IIC Bangalore, followed by postdoctoral research at Washington State University, USA. His expertise covers over a broad spectrum of areas, includes advanced metal casting, solid-state additive manufacturing, metal forming, metal processing, and tribological and surface engineering. Professor Ajay Kumar sir has a distinguished research contribution with over 35 international journals publication, 9 book chapters, 4 Indian patents, 43 international conference papers, and 12 national conference papers to his credit. In recognition of his impactful research, he was awarded the prestigious Chandran Menon Memorial Award for Applied Research and Innovative Technology for 2022-23. He has presented the 72nd Indian Foundry Congress 2024 Bangalore. He is also senior individual member of the Indian National Academy of Engineering and serves as a guest editor for several reputed QM journals include Material Characterization, LCS, Journal of Materials Engineering and Performance, Fingers and ASM, and Journal of Manufacturing Process LCS, among them. With such distinguished academic and research accomplishment, we are truly privileged to have him with us today, sir. Welcoming you, sir, for this session.
Yeah. So thank you so much for having me here, and I thank the organizer of this Atal AICT FDP program on emerging trends in advanced materials, smart fabrication techniques, and precision metrology. And I hope that all of you are getting benefited from the FDP talks which different experts are giving to you. So today I will be talking on frictionist additive manufacturing of nano metal matrix composites, and opportunities for next generation composites. Just give me a few minutes. I'm going to share these slides with you, and I will be with you then. Just give me a few minutes. I'm just opening. There is some. Yes. So I will be with you now. Okay. So hope the screen is visible to all of you. Can somebody tell screen is visible, voice is okay?
Yes, sir. Everything is fine.
Fine, and fine. Okay. So let me start the talk today. So I will be continuing this talk for almost 50 to 60 minutes. And then if you have any questions in between, please feel free to ask questions, or by the end of the talk also you can ask questions. Okay. So so the topic of the talk today is friction-stir additive manufacturing of nano metal matrix composites and opportunities for next generation composites. Okay. And myself, Dr. Ajay Kumar, Associate Professor in the Department of Mechanical Engineering at IIT Tirupati. So in the backdrop of this slide, you can see the entire IIT campus, which is the new campus, 10 years old campus in Tirupati city. And so all of you are welcome and invited to visit the campus whenever you are visiting Tirupati for temple darshan. So I will uh, cover the following topics in my talk: the introduction of the metal matrix composites, what is the friction stir processing, what is the motivation, and then I will also give you some case studies on different composite materials, what is their application, and then I will be summarizing the talk. Okay. So why metal matrix composites are are required for different applications? Why we are talking today about the metal matrix composites? So we have different features, different benefits of metal matrix composites compared to the monolithic alloys, monolithic materials. So when you talk about the composite materials, it has combination of different metals, ceramics, polymers, right? And then you combine them to bring the properties which are comparatively better than the monolithic materials. So they have high strength to weight ratio, high thermal stability, and high wear resistance, low coefficient of thermal expansion. Those are the benefits which we get from the composite materials. So the application of the composite materials are like automotives. We can use in aerospace and defense industries. Okay. Now when you talk about the composite materials, when we are saying that it is a combination of different metals, polymers, ceramics, then you also need to understand what are the different parameters which you need to control. while processing these composite materials. So you need to control the size, shape, and content and distribution of the second phase particles, which are ceramics. And you also need to see that interfacial bonding between the matrix material and the reinforcement material. So matrix material is the material which is having the high percentage or in a higher proportion, okay, and the reinforcement material which you are going to mix, right, like a solution we have a solvent and solute. So solvent is like you can compare with the matrix, and solute you can compare with the reinforcements. Now when we process these, we also have some challenges like reproducibility, uniform distribution, and sound uh, matrix and dispersive interface. So these are the different challenges also are present while processing these composite materials. Now, if I explain you about the friction stir process, there are very different manufacturing process for making the metal matrix composite materials. Metal matrix composite materials can be processed through the liquid route processing or solid route processing. In solid route, we have powder metallurgy as well. You take different type of metallic powders, ceramic powders, and do the compaction, sintering, and you make the different composite compositions. Now, the recent trend which is coming up on the additive manufacturing. So additive manufacturing, we have different type of additive manufacturing process. So most of the additive manufacturing processes are liquid based additive manufacturing process, where you are melting the powder material, or melting the wire material, or melting the rod material, right, using the some power source, right, and then you are depositing layer by layer. So additive manufacturing is a controlled localized layer by layer casting process. So in casting process, we are also doing the melting and solidification. In additive manufacturing also we do melting and solidification. But if you talk about the additive manufacturing process in solid state, can we do additive manufacturing in solid state? So if you do the additive manufacturing in solid state, then you have several advantages which are not there in the conventional or the liquid route additive manufacturing process. Because in liquid route additive manufacturing process, you get different type of defects which are almost same which you the defect which you get in the casting process. Okay, so that is why this friction stir process evolved, and this process now being evolved as the alternative for the additive manufacturing process. So there is no melting here. The material goes into the plastic deformation. So we use the friction stir tool. It is based on the friction stir welding concept, friction welding concept, where you have the friction stir welding tool. It rotates and it inserts into the material. It stirs, right? So due to the string of the tool, the material will be plasticized, and whatever compositions you want to make, you can make using mixing of the different ceramic particles as well, right? So you have different type of ceramic particles, right, and you can mix layer by layer. You can get different layers of the composite materials in solid state, right? Now the application, where is the application of this process? You can use in different structural applications. You can use in automotive applications, right? So there are some few examples where you can think of using this additive manufacturing process on solid state process. So there are different components, okay, you can think of. So this is the connecting rod, this is the piston cylinder component, right? So these are the different components you get using the casting process, right? So you can see here, this is the component. This is the aluminum metal matrix composite brake rotor, right? This is made of using the squeeze casting process. This is using the stir casting process. Okay, so there are different casting processes we use to make these composite materials. Now, what are the different strengthening mechanisms, okay, available? So if you understand scientifically the mixing of the second phase particles into the metal and how they contribute to the strength, to increase the strength of the composite material, there are different mechanisms: grain refinement, ore strengthening, coefficient of thermal expansion, and load transfer. So there are different mechanisms which are activated in the composite materials to increase the performance or strength of the composite material. Okay, I hope all of you will be aware of these processes. And so what you get is, basically what you want to get is, you want to get the high strength in the composite material, as well as you want to get the higher ductility or toughness. Okay, so if these two properties you can get in the composite materials, these composite materials you can use in very good applications. Okay, so here are few examples which I am showing you for copper composite materials which we have made using the solid state additive manufacturing process. And here you can see here the composite material is showing the higher strength as well as the higher ductility. Okay, and which shows the very potential performance. And this is the example of aluminium. So you have one side copper, one side aluminium titanium composite. So in this composite also we have seen the increment in the performance. Then another case study which we have done on aluminum alloy, A356 alloy and graphene nanoplatelets. So we have done the graphene nanoplatelets mixing with the aluminum 356 alloy, which is the aluminum silicon alloy, which is the automotive alloy. Okay, so we have done the squeeze casting and solid state processing. So this is the combination of casting process as well as the solid state processing. So this, what advantage we get is, we get the mixing of the second phase particles you can see on the surface. And once you get mixing, you can see the coating of this, and then after that we do the FSV process on it. And then what we see is, we see the uniform mixing. So this is the composite zone after the processing, and then you get the uniform mixing of the second phase particles. Okay, and this is how we can see here graphene platelets are embedded into the metal matrix. So these are the different GNPs we have embedded into the metal matrix. Okay, this is one case study. These are some of the data which I would like to show you how you can differentiate between the matrix and the second phase particles. Okay, then we also do the analysis at the atomic scale whether there is any defect on these interface between the matrix material and the second phase particles. Okay, so there is no interface, there is no defect we observe, and these silicon particles also become finer, and you can also see the strength is goes up, and even the ductility also goes up. Okay, so these are the things which we get if you do the processing using the solid state processing, right? Okay, so then we also, you can, so this is the case study which I would like to show you. If you compare the conventional casting process for making the composite materials compared to the FSP, a solid state additive manufacturing process, you have better performance. Okay, mechanical properties you can get, okay, which are not there in the. Then we also try to understand, if you do the testing, you also need to do a testing, mechanical testing on these composite materials. You need to understand the fracture behavior, how these materials are getting fractured. So most of the time, as I mentioned in the mechanical testing data, that you also get the lot of ductility. Okay, so brittle fracture, and also the ductile fracture you get. So most of the fractures are the ductile nature. So you get the lot of dimples on the fracture surface, which indicates the ductile fracture in the sample. So there are a lot of applications. So if I show you the automotive applications of these composite materials, you have the MMC disc brake rotor, you have the electronic applications, you have the cylindrical bore, you have the crankshaft, you have the different type of uh, components. Here you can see here, this is the aluminum MMC brake drum, okay, for motorcycle brake rotor. So different applications for these composite materials are available. So this is the important information which I would like to share with you, is the application of the composite materials. So you can make different type of compositions of composites and different type of process and then different type of components. So like for example, aluminum graphite composites are used in the cylinder and liner. Okay, like Ferrari, Alfa Romeo, Hero Motors, they are basically manufacturer of the cylinder liner, and they are using the aluminum graphite composites. Aluminum silicon carbide composites, the in piston, connecting rod, okay, shock absorber cylinder, and diesel engine piston, drive shaft, alumina composite, cylinder liner, brake rotor, piston crown. Okay, so these are the different compositions, process, and the component. If you do the solid state processing, then further you can enhance the properties of these composite materials. Okay, so now I would like to show you some of the other case studies which we have done on the advanced composite materials. So one composite material which we have prepared using the aluminum 7075 alloy, with mixing of the uh, polymer derived ceramics and Syria based ceramic materials. So you can see here we have used the friction ester powder additive manufacturing process. So in the solid state additive manufacturing, you have different processes name. One is the ultrasonic additive manufacturing, then you have the friction stir additive manufacturing, then you have the cold spray additive manufacturing process. So in friction stir additive manufacturing, you have another three categories like sheet lamination, you have additive friction stir deposition, then you have friction stir additive powder additive manufacturing. Okay, so I would like to show you some of the results, promising results for this process, which we can use for making the metal matrix components for next generation materials. So the concept is again same. We use the friction stir powder additive manufacturing tool, and then what you have is you have the feedstock material from the sidewise, and then due to the friction, the material will solidify, and then you will keep depositing layer by layer. This is called the substrate material, and this is called the deposit material. Okay, so then you do is you do the deposition layer by layer. Okay, so this is because of the severe deformation at elevated temperatures. Okay, which is happening because of the friction between the tool and the substrate. Okay, so now what we do is we also process the shape memory materials. So there are different type of shape memory ceramic materials which we process in the lab. So if you will be aware of the shape memory effect. So in shape memory effect, basically you have the transformations in the phases. So if you have the austenitic phase, right, you cool it down, it will deform, it will go to the twin martensite, and then if you deform it, it will become detwin martensite, and if you heat it again, it will again go to the austenite phase. So this is how the shape memory effect. Okay, and again the super elasticity also you can bring. So if you want to bring the specific properties into the composite material, you need to use such advanced ceramic materials which can impart the specific properties to the composite materials, right? So we do the synthesis of shape memory ceramics. Okay, so zirconia based ceramic and Syria based ceramics. So we use these compounds in the lab, and we do the all chemical process. We make the Syria based shape memory ceramic materials. Okay, so this is how we do the synthesis in the lab. We this is all basically chemical process we use to make these Syria based ceramic shape memory ceramic materials. Then after making them, we use the centrifuge machine, use the calcination, and then ball milling for making these shape memory ceramics into the fine powder particles. We also characterize, because once you do synthesis of these Syria based shape memory ceramic materials, you also need to understand the phases. So we to understand the phases, we do XRD diffraction, okay, on these ceramic uh, materials, and we understand the presence of the phases, different type of phases. And you can see here 101 plane, 110 plane, 112 plane, 211 plane. So they are the different study you can do of these shape memory ceramic materials. Now, the morphology, when it comes to the morphology of the shape memory. So this is the SEM picture where you can see the morphology of, so you can see the agglomerated, some of these agglomerated ceramic particles. So to understand the morphology, how they look like, what is their shape, size, all these things, we do the uh, uh, scanning electron microscopy. You can see the morphology. You can also do these particle size analysis to understand the particle size of these ceramic materials, right? So after synthesis, again another precursor we use is we use the precursor. Uh, we use the polymer precursor, which is basically the polymer derived ceramics. Okay, so polymer derived ceramics are special ceramic materials which we use for the high temperature applications. If you want to make the high temperature metal matrix composite materials, you need to use such type of reinforcements which can impart those properties. So we use these silicon based uh, precursors. Okay, so you can see here polysilicon, polycarbosilicon. Okay, these type of families we use as a reinforcement materials. Okay, and we also do the all processing and testing in the lab. Okay, so this is the again TGA, thermogravimetric analysis, where you try to see the weight reduction with temperature, whether the phase is changing or not. These all studies you can do using the thermogravimetric analysis, right? So now you need to do the synthesis for the polymer derived ceramics. So in the previously I have shown you the synthesis for the Syria based shape memory ceramic materials, and this is another ceramic materials which we are using for high temperature applications. This is polysilicon ceramics. Okay, so we have the polysilicon precursor. We use the precursor material, we use the synthesis, and even around 1400 degrees Celsius also it can retain its crystalline phase. Okay, so this is how we are doing the synthesis of the, so basically silicon carbonitride, that is a ceramic material, polymer derived ceramic material we get. Okay, and then we do the phase analysis. We get the ceramic phases of silicon nitride and silicon carbide. Okay, Si3 and 4, and Si3 and 4, and SiC. These two phases we get, which indicates the ceramic nature of this material. Now you have the reinforcement particles, reinforcement powder ready, right? So these reinforcement you can now add into the metal, right? So we have selected aluminum 7075 as the matrix material. So this is the again a small introduction about the friction based additive manufacturing process. So friction based additive manufacturing process, where you are depositing the material using creating the friction between the metal matrix and the reinforcement, plasticizing the material, mixing is happening, and you are getting the composite material. So this is how the mechanism fundamental, and this is the again 7075 aluminum powder. Okay, this is the mechanical alloying. You can see the 7075 powder, metallic powder. Okay, then we have used the 4 weight percent SMCs and PDCs. So SMCs means shape memory ceramics, and PDCs means polymer derived ceramics. So as I have shown you how to synthesize these ceramic materials, then we use these materials. So this is the machine. This is basically, you can also you must have seen the milling machine in your workshop. It is similar to milling machine. You can convert your milling machine into this type of mechanism. So we have the frictionister tool. Okay, and that tool basically process the composite material. Okay, this is the schematic, and this is the mechanism. So this tool rotates, okay, at high rpm, and it traverses from one end to another end, like that multiple cycle it will do, and then it will keep depositing the material. Okay, so you can see here, this is the deposition. Okay, you can see here, this is the process zone, and this is the build direction. Okay, so we have done around more than 20 layers. Okay, so more than 20 layers, you can see around 3.7 mm thickness. So 3.7 mm to 4 mm, 4 mm, what you call composite, additive composite materials you can get. Okay, and this is a different layer. So you can see here, so we have, this is the base material. This is the deposit layer 1, so almost 163 micron, one layer, then 195 or 200 micron, 2 year, and third year. So this is the building direction. This is the building direction. This is the cross section of the uh, of the composite metal matrix composite made by friction additive. This is the picture where we have taken on the interface. To understand the interface, you can see one, two, three, like that. You have different interface, layer by layer by layer. So these interface should not have any type of defects. Okay. So here also we have seen there are these second phase particles, like silicon particles, zirconium particles, right? They all are distributed, okay, in the metal matrix, and there is no agglomeration of these particles. Okay. So we have seen the better distribution compared to the casting process, and that is why you will see the better performance from this composite materials. Okay. So we have done the elemental mapping. Why we do elemental mapping? To understand the presence of all elements, right? To verify the presence of all elements. We do the skin electron microscope, energy dispersive spectroscopy, right? So through energy dispersive spectroscopy, you get the composition, different type of elements present in the composite material. So whatever you mix, right? You should be verifying whether it is present or not. Okay. So that is how you verify, and then you try to understand the again we have the different technique called the electron probe microanalysis, and through electron probe microanalysis we try to understand under composition more accurately and layer by layer deposition. This is aluminum, this is magnesium, this is copper, this is silicon, this is cerium, zirconium. Okay, so each picture shows the percentage of the element present in the composite materials. Then now you go to the atomic scale. Okay, you try to understand the crystallography, right? You need to understand the grain boundary engineering, how the microstructure. Okay, so this is the microstructure you get. So we are almost getting 6.43. So you can consider around 6 micron grain size, okay, which is very very small grains. And if you can get this type of microstructure, the material performance will increase compared to the casting process. So I hope that most of you will be aware about these dynamic recovery, recrystallization, and dynamic rectifier mechanisms. Okay, so and so basically these are the fundamental mechanisms in any. If you have done the metallurgy course, you will be understanding these dislocations. You will be understanding the what is dynamic recovery, what is recrystallization. Okay, then low angle boundaries and high angle gain boundaries. Okay, so we try to understand this thing using the electron backscatter diffraction technique, right? You can calculate how much is the misorientation distribution, like 1 degree, 5 degree, 15 degree. Okay, what is the fraction? Based on that you can calculate like which strengthening mechanism is more active in the composite materials. Okay, so this is the misorientation angle. So most of you will be aware, generally if the misorientation angle between these two grains is between 1 to 15 degree, you say it is low angle grain boundary, and if it is more than 15 degree, you say it is high angle grain boundaries. Okay, this is how you can differentiate, and then you can also see this is the grain boundaries. So you can see clear grain boundaries, grains, right? And different size, and different orientations. Okay, so basically this comes under crystallography. If you study this crystallography, it is very useful for advanced studies of these composite materials, right? Then you go to the chem map and pole figure. So basically here we try to understand the texture of the material. So what is texture? Texture means you have the preferred grain orientation in the material. Okay, so you try to quantify these grains, quantify the texture. Okay, so if it is a strong texture, then it exhibits the anisotropic behavior during plastic deformation. So I think you will be aware about anisotropic and isotropic properties. So you want to bring those properties into the composite materials. So based on this analysis, you can identify that these composite materials are having anisotropy or isotropy, which is dominating more. Okay, these things you can study. Now, another thing which you will be aware about is these transmission electron microscopy. So transmission electromicroscopy, basically we study about the dislocations within different type of strengthening mechanisms using this technique. Okay, so you can see here in this first picture, these are the subgrain boundaries, and you can see here the some of the second phase particles and some of the precipitates are present into the compound materials. Okay, and then you must be knowing about dislocations. Then when you have dislocations, right, through dislocations also you can get strengthening into the compound materials. So if dislocation interacts, right, due to the interaction, right, you can see here there are dislocation lines, and when these dislocations interact with the second phase particles, they hinder the dislocation motion, and then you get the more strength into the compound materials. Sometimes the dislocations also can be tangled, right? So when dislocations are tangled, right, your strength performance of the compound materials also will increase. So these are the advanced characterization techniques at the atomic scale. You will try to understand the what is happening at the atomic scale. Okay. Then this is the distribution. This is the elemental analysis, precipitation phase analysis through the uh, high high angle annular dark field scanning transmission electron microscopy. So we say it is HAADDF. So it is a high angle angular dark field imaging. Okay, so this also we do in the transmission electron microscopy, and this shows the distribution of the second phase particles. Okay, and different type of precipitates into the composite materials, because based on this only you can know, you can do the proper study of your composite materials. Okay, and different type of sometimes precipitates also form, that also you can identify from this. Now you will be aware that different type of strengthening mechanisms are operating. I showed you in the beginning slide. So grain boundary strengthening is one of the strengthening mechanisms. So most of you will be aware about the Hall patch equation. Hall patch equation says that uh, if you can refine the grains, refine the microstructure, you can improve the strength of the material, right? So that is one parameter this solid state processing can do. It is basically refining the microstructure. Second strengthening mechanism is the dislocation strengthening. Dislocation, which I have shown you here. So you have a lot of dislocations lines here, a lot of dislocations are entangled here. So basically these dislocations are entangling, and they are basically providing the strengthening to the compound material. So this is how you can calculate. So you can theoretically you can calculate, and practically also you can calculate and verify both are matching. Then you have the precipitate strengthening. You are having the precipitates, right? So you will be knowing about the Orovon looping. So if you have the Orovon looping, right, then you the precipitates, a lot of loops are formed and they grow, right? So they also provide the strengthening to the composite materials. Clear? So this is how these strengthening mechanisms operate, and then you can identify which operating machine. And then another is strain hardening. Okay, so strain hardening, and another thing is when the dislocation density increases, right, into the plastic deformation. So this is again when a lot of dislocations are are entangling, right? Dislocation interactions is happening. Because of dislocation interactions, the strain hardening takes place. Okay, in any material. So this is how you can identify the strain hardening mechanisms. Then you can do the testing on these materials, like we have done the hardness test, we have done the tensile test, right? So micro hardness test, basically it's the localized plastic deformation. You try to do the indentation on the composite surface, right? And then you do the localized plastic deformation, and you get the hardness number, right? Based on that you see, and we also do the, then you can do the mechanical testing of these compound materials, right? So this is how you can see the increasing the strength, increasing the ductility, right, on these compound materials. Okay. Then you also need to understand when you do the testing, sample will be fractured. When sample will be fractured, you need to understand how it is being failure, whether it is ductile nature or brittle nature. All these things you can identify using the fractography technique. Okay. So now what do I? So now I will conclude here. There is thermo. This is called the thermomechanical processing. Okay, thermomechanical processing, it is causing the severe plastic deformation in the material. Okay, and then you also need to understand the tool geometry, rotation speed, translation speed, which I have shown you in the schematic, process schematic, where you have the tool which rotates, transverse, and then insert into the metal, and then through the characterization techniques, I have shown you the different type of strengthening mechanisms, right? And fractography I have shown you, right? So all these datas I have shown you, and you can see a lot of improvement compared to the conventional process. Okay, there are many manufacturing process, but you need to improve the overall performance of the composite materials based on the application. Accordingly, you have to select the process. Okay, so this is not the only process. There are several processes, but you have to select the manufacturing process which is more suitable for that particular product. Okay, now another quick thing which I would like to show here is, we have there are other post processing techniques which you can use. So we have done the multi-pass processing, like that you can see here the post processing techniques you can do on these composite materials to refine the microstructure again, right? And this is how we can make the composite materials. Okay, and this is how we do the study. So this is the composite zone. So you have to optimize the process parameters. Okay, and then again you have to make sure that the strength and process parameters are correct. We also have done the corrosion studies. Some of the composite materials are good for corrosion resistance. Okay, because these composites you can use for the applications where you have more corrosion possibilities. Okay, that is how we also study the corrosion. So this is all published work. We have published this work before, and we have concluded this. Okay, so I hope that now you have got the clear picture that how you can use the solid state techniques for making the composite materials. Now, in the first slide, I have shown you uh, about the three things. One is the dispersoid. Dispersoid means second phase particles. Then you have the, what do you call, their shape, their size, their distribution. Then the interfacial bonding. Okay, interfacial bonding is also important. Okay, so this is how we do the uh, processing for the composite materials using the solid state. So basically, these are the next generation